Hey guys, this is Alan Gregg here to continue our FE preparation, and to do that, today we're going to talk a little bit about op amps. An operational amplifier is a high-gain DC amplifier. The gain of an amplifier is the ratio of the output voltage signal to its input voltage signal. An ideal op amp has the following characteristics: infinite input impedance, zero output impedance, an infinite open loop gain, and unlimited bandwidth. Now let's talk a little bit about what those mean for the circuit. The infinite input impedance of the ideal op amp means that no current from the supply flows to the internal circuitry of the op amp. So while there are things going on in the inside of the op amp that makes it do what it in fact does, we don't have to concern ourselves with those things when we're analyzing the effect of the op amp on the overall circuit in which it's used. The zero output impedance of the ideal op amp allows the amp to supply as much current as necessary to the load. And the op amp can amplify signals with any frequency range, from DC, which we consider to have a frequency of 0 or 1, to the highest AC frequencies. The ideal op amp gain acts on the potential difference between the inverting and non-inverting terminals of the op amp. And the assumption of an ideal op amp is very practical because its characteristics are in fact very close to those in a real op amp. So we can use these assumptions to make the circuit analysis a lot easier, and the calculations become a lot more simple as well. Now, the top bullet point on that slide right there, I want to look a little bit more at the ideal op amp gain acts on the potential difference between the inverting and non-inverting terminals of the op amp. Let's take a look on our whiteboard at what the inverting and non-inverting terminals are. So I know we've got a lot going on this page here, but I want to draw your attention to this picture. And when we say inverting and non-inverting inputs of the op amp, we're just talking about these. So this input that's attached to the negative symbol there that's our inverting input, and this one with the plus sign is our non-inverting input. So I just wanted to make sure it was clear what we mean when we talk about those things. All right, going back to our slides, let's talk a little bit about, let's back up, because I don't know that we've made it completely clear how an op amp can be used and in a practical circuit. So let's go back to our whiteboard now, and let's take a look at one of the common configurations in which you'll see an op amp used. This configuration has a voltage supply connected to the negative input of the op amp, and the positive input of the op amp is connected to ground. Now, when you see this, first of all, this is called a non-inverting op amp, and that's because the power supply is going to the non-inverting terminal, and the gain of a non-inverting op amp the gain, which is by definition the ratio of the output voltage to the input voltage, for this particular configuration is equal to negative R2 over R1. And let's find R2 and R1 on this. This will make a little more sense. So here is our R2, and here's our R1. And so to figure out the ratio of the output voltage to the input voltage, our output voltage is right over here. To figure that out, we just take this resistance here at R2 and divide it by the resistance at R1, and then we've got our gain. Now let's talk about what this negative sign means. The negative sign here doesn't mean that the signal itself, or the voltage, has become negative. This simply indicates that there's been a phase shift. There's a 180-degree phase shift between the output signal and the input signal. Next thing you might be wondering is, how in the world this came about? And there are several things you got to take into consideration to figure that out, and let me back up a little bit. To figure this out, you have to use nodal analysis. Here at, let's pick another color. This is getting crazy. All right, we've got a node here, we've got a node here, and we've got a node here. And so we've got currents running here, here, and through some pretty hairy nodal analysis, which we could do, but we're not going to do for this video. Consult your electronics book for further detail. But through that and the assumptions mentioned on our presentation, let's see if we can find those. Let's go back to these assumptions of an ideal op-amp. I believe this is on slide 2. An ideal op-amp has the following characteristics. Infinite input impedance. This means that the impedance of the currents going into the op-amp is so great that no current actually goes into it. So it's all going to go through, from the voltage supply through the first resistor to that first node at V1, and then through the second resistor to Vout. It's got zero output impedance, which means there's no voltage drop from Vout to ground. It's got an infinite open loop gain, which means that the difference between V1 and V2 is nothing. If we have an infinite output gain, the difference is nothing, which is very, very important in finding this gain value that we've got on our whiteboard, because it allows us to apply what we call a virtual short, which essentially results in this on our whiteboard. All right. So that voltage between this point and this point, the potential difference is nothing. And that's very important to get there as well. Now, I strongly encourage you to take a look in your electronics book to check out the examples of how these gain expressions are derived. But we're not going to take the time to do it here. I hope that's okay. The next thing I want to do is I want to change a couple of things in this, and I suppose I could try to erase all the mess I just put on there. I will do that, actually. Made that decision now. All right. Another very common use for the op-amp is in a non-inverting configuration. And the difference between the inverting configuration and the non-inverting configuration is the location of this voltage supply. So I'm going to erase it. And we're no longer going to have that voltage supply connected to the inverting input. Instead, we are going to have it connected to the non-inverting input. And when we do that, and again, using the assumptions we mentioned earlier about the ideal op-amp, and then performing some nodal analysis, we get a new expression for the gain of this. And here, again, this is a non-inverting configuration because the voltage supply is connected to the non-inverting input. The gain is equal to 1 plus R2 over R1. And again, I don't know if I mentioned this explicitly, but the gain is the output voltage, the ratio of the output voltage over the input voltage. So that's the factor by which we're amplifying the input signal. All right, I know a lot just happened on this page, and it was pretty ugly. I hope that it helped to some degree. Again, don't rely on this as your exclusive study source or study resource. I encourage you to look into it yourself, and good luck on the FE.